Good afternoon, everyone. It's my great pleasure to be here today. Today I'm going to talk about a bit about something different about using UHPC for repair for steel piles. So I'm going to start with the issue, and this is an issue many of the states on the Midwest has. So we have a lot of bridges that were constructed using steel piles, H piles. So these are just few examples over here. Some of these piles using for the abutments. Some of those are used for in conjunction with the sheet piles. And maybe 10, 15 years down the road during service life, this is what we have. So you see some of these pictures over here. This is a about 15 years old bridge. So this is a web. This is another one. Both those are in St. Louis area. And I don't know where are those located, but I got those from different sources. And then the one over here, also in St. Louis area, you have also the web and flanges. Both are severely corroded. And you can think about this one over here, where you literally can cross your hand from the web. So this is the issue that we have, and it's not a limited issue. In Missouri, we have 700 bridges like this. And out of those 700, we have 300 bridges where the web severely corroded. And out of those, 80 where you need to reduce the capacity of the bridge because of the corrosion. So it's a few $1 billion that may end up with something like this. So this is what we end up. So MoDOT is interested to look at different options for repair and try to look at minimizing the cost. So we're looking at different things. We have this project is twofold. The first one, would like to know how much is the capacity after the corrosion, because they don't want to repair the 700 bridge. So they would like to assess what is the remaining capacity. And on the second fold is how to repair. So for the capacity, we did two things. We went to those of one of those bridges where they are going to demolish the bridge, and we back up some of these piles. So those are some of the minor corroded piles, but we have also some severely corroded piles that we get from the same bridge. And also we have some others where we have an S-belt piles where we did some reduction on the cross section to mimic the reduction on the cross section. So it's more like an engineering reduction on the cross section. Some of those where we had reducing, we have a void on the web, cut on the flanges, or even just a reduction on the thickness. So these are just give you an idea some of the cross section that we reduced. And then the other parameter was how what is the length, what is the extension of the corrosion over here. So we also look at different extension, starting from 6-inch all the way to 24 inches extension of corrosion. So test it up. This is a full-scale testing of the piles. Most of these piles, in Missouri at least, they are 10 by 49. Typically, those are grade 36, and some are grade 50. So what we have over here, this is our pile, the one, the white specimen over here, and then we would have a bend joint, and then we have, this is a self-sustained test setup. So we apply the we have 6 post tension bars over here, and then we have 2 actuators over here. So we apply the load to the using the 2 actuators, one reaction going to the red beam over here, and using the post tension going back to the other red beam, and then squeeze the pile in between. And the other reaction from the actuator going to a movable black beam over here. So this black beam is moving on rail. So you have a wheels over here on the top and bottom to ensure that this black one over here, it's also moving on the rail over here. So to ensure this black beam over here moving parallel to the red beam, so we don't have any twist on while we're applying the loads. And then this is a bend. So for the bend, to mimic a bend, the issue, many if you look for the literature, many people try to use like cylinders, like to represent a bend for something like this. We did this for the first test, but because you do kind of a random, some of these specimens have a random corrosion, you really don't know where is the buckling would happen, because now your minor axis is really kind of, at sometimes it's not the X or Y. So we move to manufacture this one over here. So we have a half a sphere connected to a blade, this blade connected to another shoe over here, this shoe is the one over here, the red. So this is the first part, and then on the second part is this is connected to our test setup. So these are the two parts, and then we have grease in between to have more or less like a bin connection in both sides. So this is testing one of the conventional one after doing the corrosion. So this is the testing. This is different cross sections, and then we did some finite elements models, and then we start for repair. So the first repair option, we look at one of the conventional repair that has been used by other DOTs. So what they do is they have carbon fiber wraps, and they fill with some sort of either concrete or different grout system. So we start with this one over here. The whole idea over here, MoDOT would like to have a more or less like a straightforward solution, a one-size-fits-all. They would like actually to bridge the corroded section. So we would like to have the load. The load is bridging through the retrofitting over here and go back to the original section back again. So they try to avoid the passing the load through the corroded section at all. And this is why we have this lengthy repair over here. So we start from looking at what is the friction and what is the cohesion between concrete and the steel binds. So on the concrete side over here, we looked at different sort of concrete. So we start with conventional concrete, high early strength, UHPC. We looked at polymer modified concrete. We looked at geopolymer concrete, thermal cured, and ambient cured. So we looked at 6 or 7 different types of concrete, and for each one of those, what we have the steel pile extending all the way over here, and then we have a 2-inch gap over here, and then we push the steel pile versus the concrete, and based on this, you'd come up with a slip versus stress for different types of concrete. So this is just to give you an idea here about the testing. So this is the conventional cracking, what you would expect. Different strengths of the concrete as well, different lengths. So this is another one over here where we use the carbon fiber and the grout over here. One of the things is one of the question whether to use steel studs or without steel studs. This was also one of the things that we investigated, and this is just give you a flavor of the results. So what we get over here, for example, you have on the beginning over here you have a full bond. Everything is elastic. Everything here is elastic at the beginning, and then you start to get some slip. You reach the peak loads, and then you start to have the reduction. The good news, we're able to transfer 100% of the capacity of the pile through the jackets. So this is very much the capacity of the jackets. So we yielded the pile actually without collapse the jacket itself. So once we have done with this, we went and repeat the same test. So now you. So now we moved actually the if you see over here, we moved the the section. So inside the pile over here, you have a severely corroded section. In fact, this pile was originally tested as a reference specimen, and after this, we just straighten up the pile with all the residual display, with all the residual stress on the pile, with all the stuff, and still capable of whenever we have the wrap to recover the capacity of the pile and having the rupture occurred on a different section over here. Now, where is the UHPC? So the first option was to look at the wrapping using carbon fiber and different types of concrete. The second solution here is to look at UHPC. And for UHPC, they were interested in 2 different options. This is still work in progress. So the part of the UHPC still, we just started a few months ago. So we look at 2 different things. The first one is to have a precast elements. So they dream of something that would be on their backyards. Whenever they get a call, there is a new pile corroded, then they would have the maintenance guys have these precast elements delivered there and fixed with bolts. This is their objective over here. So we look at different shapes. So this is one of the shapes over here, the C-sections that hopefully would be installed within the pile over here, so it fit within the pile. And then we look at also different plates that can be installed. And when I'm talking about the plates, we are sheeting from also one of the current practice where they use the steel plates. But instead of the steel plates, because it's corroded sections, adding steel would not really solve the issue, would not really lengthen the life of the pile too much. So we use the UHPC plates over here. We looked at the anchorage, different anchorage system. So a lot of details also for the plates over here. We look at different thickness, starting from 1.5 inch all the way to 3 inches. One of the limitations over here, looking for something practical. So they would like something that can be easily carried out by on maximum 2 workers. So the weight was really one of our big concern for these plates. So this is why we try to reduce the thickness. And reinforcement. So some of these UHPC, so they don't want to use any over-the-counter mix. So we try to develop a mix that's using our locally available material. So this is the best that we can come up with. And this mix over here gave us 20 KSI after 3 days. So those were cured 24 hours in steam curing, 24 hours steam curing at 70 Celsius, and then we put those for another couple of days on a chamber where it's subjected to some moisture. And then some of those are just UHPC plates. The others, we installed some of the carbon fiber grades. So some of those, this is the carbon fiber. So some of those were just a single layer of carbon fiber on the middle of the plates. Others where we have layers. So we have a first layer, install the carbon fiber, another layer of concrete, and then layer of carbon fiber, and then a concrete. So the total for this 2 layers of carbon fiber, the thickness was about 2¼ inches, and we have 2 carbon fiber on those. So we have a cover of 0.75 inch, 1.5, and then 0.75 inch of carbon fiber. And also looked at for cast in place, the whole thing over here would like to evaluate how much you get from the cohesion and how much you can transfer through the steel studs. So we have those cast in place just to help us evaluate the cohesion component over here. And we have those over here with the precast. And then we started from, as we did with the wrapping, we start from scratch. We also have the different bolt size, bolt distribution, diameters, and we start looking, okay, if we have, pushing this and we have the gap over here, how much for that you can transfer. So as you would expect, the first mode of failure would be if you don't have, enough bolts, or the thickness of the diameter of the bolts is not enough, you are shear off the bolts. And this is the force versus displacement that we get. Very typical for this sort of failure. The second one, you start to see local damage over here on the UHPC. And then some of the specimen, you have the splitting over here. So we start with some splitting, and then after you have enough splitting, you also trigger some of the local liquid failure. And if we have 2 layers of grid of carbon fiber, you have 2¼ inch thick plates, we're actually able to reach the capacity of the bolt. The capacity of the METS machine, and we're not able to proceed any further. This is why we stop over here. So now we are moving the whole thing here to the large scale test setups where we can reach roughly 1,500 kips. So as I mentioned, this is still work in progress. So far, we're able to develop a UHPC using locally available materials. We show that there is a potential to use these very quick to use precast UHPC plates to repair some of those piles. Thank you to our sponsor over here, Missouri DOT Mid-America Transportation Center, Skyline for the steel piles, 5, and Quick Wrap for the carbon fiber. Thank you so much for your attention.